Hello everyone, my name is Anastasiia and today I will be the voice behind the slides. Together with Eva and Helmut, we found an exciting new method to synthesize floating point loop invariants using counterexamples and simulation that I'm going to tell you about. So usually when we analyze programs with loops, we statically do not know how many iterations the loop will take. So we need a way to reason about loops as a single unit, which is an inductive loop invariant, a property that holds on a loop entry and after every iteration of it. In general, such an invariant can be of an arbitrary shape, whatever helps to prove a property that you're aiming for. For floating point loops, it makes sense to have an invariant in the shape of ranges for values of variables. It is helpful for safety verification when you need to prove that the variable does not reach some unsafe state, unsafe value, and ranges are also prerequisite to bounding rounding errors. Let's have a closer look. Say for a loop in our example, we want to have an invariant and our prerequisite is that x and y values are between 0 and 0.1. Those are shown as a green box on the right side. Then an invariant would be a larger box that bounds all of the values that are reached by x and y inside the loop. However, just having a box is not sufficient for an invariant to be inductive. So we need an additional constraint that here is expressed in the form of polynomial inequality. We noticed that this is often the case, that this additional constraint is expressed as an ellipse. So for the purpose of this talk, I will consider invariants of such a shape. Ranges of variables intersected with ellipsoid that is expressed as a polynomial inequality. Now assume we are given such an invariant and then we know precondition for the loop and we are aware of the loop body. Then checking whether this invariant is indeed inductive is easy. We can do it by querying an SMT solver, such a query. However, coming up with an invariant is in general non-trivial. There exist plenty of techniques that come up with invariants, and the variety is huge, starting from manually coming up with an invariant by just looking at the code, then more advanced techniques as using abstract interpretation with widening or recurrence-based techniques. The list goes on. However, most of these techniques only consider real or integer numbers, which means that invariants that they come up with do not necessarily hold for floating point loops. Among the techniques that can handle floating point loops soundly, a lot of them can only handle linear loops because of the underlying algorithm. Some of these techniques also require a postcondition, which in our case means that we need to come up with the ranges in order to find the ranges. Another limitation is techniques that require a fixed template for the invariant. And last but not least, some of these techniques can only come up with trivial invariants when analyzing nonlinear loops with floating points. Given such a starting point, what were the challenges that we had to face? First of all, we want to have a tight invariant, such that we can prove something useful about our loop. Since we're talking about floating point loops, and we know that we want to have ranges as our invariant, and we will have an additional constraint in the shape of a polynomial inequality, what we essentially need to come up with is coefficients for the polynomial and ranges. Theoretically, we could ask an SMT solver for a model of these coefficients. However, today's SMT solvers cannot efficiently do quantifier elimination, especially for floating point theory, where even verifying that an invariant is inductive already takes very long and therefore is not practical for our purposes. As I said, exact reasoning is not feasible. However, our key observation was that it is also not necessary. There are actually several inductive invariants for the same loop, and we only need to find one of them. And because we do not need to hit this one particular invariant, we can introduce some noise by abstracting the errors away, simulating loop iterations, and using synthesis methods that do not necessarily provide optimality guarantees, such as counterexample guided synthesis. Let me briefly remind you what is the counterexample guided inductive synthesis. In essence, it's a generate verify loop. First, the synthesizer comes up with a candidate invariant, then it checks it using, for example, an SMT solver, and then if the solver confirms that the invariant is inductive, then the synthesizer is done. Otherwise, it returns back to the generate step. And since coming up with candidates randomly is not practical, CEGIS uses a counterexample in order to refine the next candidate. Applying a standard CEGIS to floating point loops does not work. As I already said, even the verify step can take hours for a simple loop and therefore is not scalable. But since we do not need to use exact reasoning, we can abstract rounding errors away and use the real valued query to verify our invariant. In order to compensate for this additional noise, we need to add some kind of smart generalization from a counterexample returned by the solver. So what we suggest is to use simulation. And after we use the simulation, we also need to return back to our shape, so we're using a noisy polynomial fit. Now let's go through all of these steps one by one. How do we initially guess the coefficients? To make the first guess informed, we simulate the loop by randomly sampling points from the precondition ranges and iterating loop n times starting from each of these points. Here the precondition is shown as a green box, and all of the blue dots are the simulated values. Now, these values give us an under approximation of all of the values that are seen inside the loop, and therefore we know that these points must be covered by the first candidate invariant. Since at the moment we only consider elliptic shapes, we only need the values at the borders of the sampled set. Therefore, we compute a convex hull and significantly reduce the number of points to consider for further steps. Next, we fit the polynomial from the convex hull using either the minimum volume ellipsoid or the least squares method. And for ranges, we simply take maximum and minimum values among those seen in the simulation. Obtained polynomial is necessarily noisy. First, the fitting methods are themselves inaccurate, and here you can see on the picture on the right that some of the blue dots are not covered by the fitted ellipsoid. Secondly, the polynomial only considers a fraction of all possible loop iterations, so we want to include more iterations. To get rid of the noise, we scale and round the polynomial coefficients and do the same for the ranges, rounding outwards. Given the candidate invariant, we are coming to the verify step. As I already mentioned, floating point SMT theory is not scalable enough for repeatedly calling it inside a loop. We actually tried querying an SMT solver with a floating point query for a simple loop, and it took hours to finalize. That is why we abstract rounding errors of floating points with real values. And for that, first we compute rounding error for current ranges, given an expression, ranges of variables that participate in this expression, and a floating point precision. We feed this information into an analyzer that outputs a rounding error. And then the actual abstraction would be to add this error as a non-deterministic term to our original expression, and the range for this non-deterministic term is defined by the size of the error returned by an analyzer. Using a non-deterministic term to abstract rounding errors is not new. However, the approaches that we are aware of are using a universal constant that works for most of the loops, and we over-approximate much less because we compute an error specifically to the ranges and an example at hand. For our example, the candidate invariant was not confirmed, and the solver returned the counterexample. Here by counterexample, we mean a point that itself satisfies the invariant before the loop iteration, and in one loop iteration reaches a point that violates the invariant. On the slide, this is shown as a red dot. Using just a single counterexample is in most cases not enough. We already introduced additional noise at the generate and verify steps of our algorithm, and additionally, the counterexamples that we get from the solver are essentially random. So we cannot rely on just a single counterexample. This will skew the shape and might prevent the algorithm from converging to an invariant. The crucial point is to use generalization. Our algorithm uses several ways to generalize from a counterexample. First, we can ask the solver to return an additional counterexample that is at least at some distance from the original one. Additionally, we can use nearby points. By nearby points, I mean points at a constant distance from the original counterexample. And from those, we would only take the points that already satisfy the candidate invariant, such that we don't introduce unreachable values. Last but not least, we may benefit from the fact that our polynomial inequality has a shape of an ellipsoid. And then we take points that are symmetric to our original counterexample with respect to axis of symmetry of the ellipsoid. Our algorithm allows to use any combination of these generalizations, for example, all of them together. However, it is not necessary to use all of them, so for simplicity, I will only use symmetric points in this presentation. Now, once we obtained all the additional points, the last step of the generalization is to simulate the loop starting from these points. Since we are looking for an inductive invariant, it must hold not only for the new points, but also for all of the points obtained by further loop iterations. We then return to generate step and obtain a new polynomial and new ranges that include simulated points and all additional counterexamples. Here we show the new candidate invariant in the dark blue. And then the loop continues to verify whether this is an inductive invariant. We repeat the generate verify loop until either the invariant is found or we reach the maximum number of iterations. For the example loop, the algorithm needed 7 iterations to arrive to a final invariant. And here on the graph, the later iterations are shown in darker shade of blue. We have implemented our algorithm in a Python library called Pine. For computing rounding errors, we used a tool called Daisy. We also determined a reasonable default setting in which we initially sample 100 points and then run 1,000 iterations of loop from these points. We round coefficients of polynomials to 2 decimal points and ranges to 1 decimal point. Out of all generalizations from counterexamples, default setting only uses symmetric points. And once all additional points are obtained, the default setting would simulate 500 iterations of the loop from these points. We also implemented an additional optimization where we first find a real valued invariant and only then we confirm that this invariant also holds for floating point loop. This allows us to save time and potentially come up with tighter invariants, and in practice we noticed that for 97% of the cases we do not need to recompute the invariant, meaning the real valued invariant is also confirmed for floating point loop. In our experimental evaluation, we wanted to answer several questions. First, how does Pine compare with other tools? Second, is the running time reasonable? And how sensitive Pine is to all the input parameters. We have performed the experimental evaluation on 30 benchmarks that implement simulations of dynamical systems, controllers, and filters. These benchmarks contain infinite non-nested loops with at most one conditional statement, and they include both linear and non-linear computations. To compare with state-of-the-art tools, we were looking for the tools that can handle floating point loops soundly and can also output an invariant in the shape of a polynomial inequality. We found two such tools, SMT-AI, that applies policy iteration with ellipsoid abstract domain, and PLAT, that analyzes a loop body by computing its eigenvector. Since we want to find tight invariants, we will be comparing a volume of the invariant, and here it is shown on a logarithmic scale. When we ran PLAT on our benchmarks, we noticed that for many of them, it was not able to return any invariant, and here these benchmarks are shown with a volume infinity. Then we compared with the results of SMT-AI, where unfortunately we were not able to install the tool, so we computed the volumes of the invariants that are presented by the authors of the paper. As you can see, SMT-AI is doing a bit better. Compared to these two tools, Pine is able to synthesize much tighter invariants. On average, it is 12.4 times tighter for linear benchmarks. Because Pine is using random simulations, we ran our tool 4 times, and the blue bars represent average values, and the maximum and minimum values are denoted by the black error bars. As you can see, for most of the benchmarks, even the largest invariants returned by Pine were still tighter than the invariants returned by PLAT or SMT-AI. And for nonlinear cases, neither SMT-AI nor PLAT were able to produce any invariants, whereas Pine produced tight invariants for all 6 of our nonlinear benchmarks. The next question we wanted to answer is how efficient is our tool? We measured that on average Pine takes 25 seconds per benchmark, and the maximum running time was 55 seconds, which I would argue is reasonably fast. Last but not least, we wanted to know how sensitive our algorithm is to input parameters. So we ran Pine on 1296 different combinations of parameters and analyzed the ones that resulted in synthesized invariants across all benchmarks. For our experiment, we had 183 such configurations. Here, the graph depicts a proportion of different settings among these successful configurations. From this, we concluded that our method is robust. As you can see, for most of the parameters, the proportions are almost even, which means that it doesn't matter which individual parameter you will use, there will be a configuration that would lead to successful invariant generation. Our next key observation was that we should round a polynomial to 2 decimal points and ranges to 1 decimal point. Also, we noticed that all of the generalizations are equally useful. It is not important which of them we are using. However, it is important to use at least one. 92% of successful configurations used at least one generalization. And lastly, the simulation from counterexamples and additional points is essential. There was not a single successful configuration that would not use this simulation. Out of all successful configurations, we selected one that resulted in invariance with the smallest volume across different benchmarks, and we took this as our default setting for the algorithm. Note that differences in volume between top 5 smallest volume configurations is about 2%. So actually we could have selected either of these configurations as default and we would be getting comparable results. To conclude, I would like to remind you main takeaway points. We introduced the first method that can soundly handle nonlinear floating point loops and produces much tighter invariants for the linear ones. We achieved this by extending CEGIS framework with using noisy polynomial fit for candidate invariant generation, abstracting rounding errors for the verify step, and generalizing from counterexamples and simulating the loop when refining the candidate. Our implementation is available open source. If you want to check it out, it is available on GitHub. Follow this link. Thank you for your attention.